So welcome everyone. A big ups to everybody that is watching me. This is another episode of BJ's Physics Classroom. This section is going to be the continuation of the momentum and the Newton's laws of motion. You remember the last time we met on that topic, we looked at the Newton's laws of motion and linear momentum. So today we are going to continue with linear momentum and collision, which will end that particular topic. So stick and stay with me whilst I take you through it. But in the meantime, if you haven't subscribed to my YouTube channel, please subscribe. BJ Online, that is my YouTube channel. And whilst you subscribe, please turn on the notification button so that anytime I post a video, you will be able to receive it. Thank you, and let's begin. So we first begin with coefficient of restitution. We begin with coefficient of restitution. This is a term which is associated with collision and linear momentum. So when we say coefficient of restitution, what do we mean by that? The symbol for coefficient of restitution is E, and it is defined as the ratio of the velocity of approach, the ratio of the velocity of separation to the velocities of approach. You know, for a system of colliding bodies, M1, M2, moving with velocities U2, and U1, that engage in collision. Before they engage in collision, they probably approach each other and they engage in collision, because if they don't approach each other or one of them doesn't bump into the other, there can be collision. If two bodies move separately in their own ways like this, they won't collide. So when we say the ratio of the velocities of separation, we are talking about their final velocities. When we find the difference in their final velocities, so this is before. Now, after collision, we get M1 going into V1, and then M2 going into V2. After collision, they will have velocities V1 and V2. Before collision, they have velocities U1 and U2. So the ratio of the difference in velocities after separation to the difference in velocities before separation, that is what gives us the coefficient of restitution. So this is the definition for coefficient of restitution. Remember, velocity is a vector quantity. So anytime we use this formula, if the two bodies move such that they move in the same direction and collide, then their velocities are all positive like this. We always take into consideration the direction. But in a situation whereby the two bodies move, whether before or after, like this, U2. In this case, the two bodies approach each other. So while this one is moving in the positive x direction, this one is moving in the negative x direction, because the M2 is moving in the opposite direction. The initial velocity of this will have to be negative. We'll have to take into consideration the direction of the velocity of this. If in a situation whereby they collide, which is hardly possible after collision, they will move like this. Let's take it that that can also happen, V2. Then it means that this velocity too will have to be negative. But this one doesn't really happen. So most of the times it happens with the initial velocity. So all that I'm trying to say is that when the two bodies collide such that their they initially move in opposite directions, then one of the velocities must be negative. If they initially move in the same direction, then both velocities will be positive. But the formula is such that we find a change, so these negatives are always here. So that is how we deal with coefficient of restitution. Coefficient of restitution. In a rebound situation, a situation whereby an object hits and bounces off, an object hit the ground and bounces off, then what is going to happen is that, in a rebound situation, an object moves, hit the ground with a certain velocity. Let that be the initial velocity with which it will hit the ground. After it has hit the ground, it will bounce off. So that will be the final velocity v that it will use to bounce off, like this. The body will get to probably this point. So the body will cover a certain height, capital H, with which it will hit the ground. The body will cover a certain height, small h, that we call the rebound height, small h. In this situation, when we make changes to this formula, we are going to get negative E is equal to, because the ground, remember it is only the body that is moving. The ground is not moving. So because the ground is not moving, the V1 and the U1s will go to 0. So we are going to have V over U. As simple as that. Because it's only one body that is moving. Only the object that is hitting the ground and bouncing off. So the coefficient of restitution formula becomes like this. How do we bring in the height? U is the velocity of impact with which the object hit the ground. And that velocity of impact, U, is given by 2gs. Because of time, I wouldn't be able to go through, but you have done linear motion. And I know you know that V squared is equal to U squared plus 2gs. So when the velocity, when the V is 0, you make U the subject, and then you finally get this one. This S now becomes the height H. Let's call this equation 1. For this rebound situation, the velocity V that it will be given to the body to move up, at the maximum height, the final velocity is 0. In this case, we are looking for this U, this V, which is the initial velocity. That will give us square root of 2g small h. Let's call this equation 2. So when we put these two values into this, that is going to give us negative E is equal to V square root of 2gh all over square root of 2gh, capital H. So 2gh, the 2gh can cancel out because we can rewrite this formula as negative E is equal to square root of 2g times square root of h all over square root of 2g times square root of h, capital H. So when this one cancels this, finally we get coefficient of restitution negative E is equal to h over h. But because height is a scalar quantity, when you consider the motion, you consider the height as displacement. While you take into consideration the direction, then you can bring a negative because the E is supposed to have a positive value. But if you consider the h as height, which is a scalar quantity, then you ignore the E, this is negative. So that the coefficient of restitution value will give you positive. Good. Now, coefficient of restitution has three interpretations. It has three interpretations. So take note of this formula very well. For a rebound situation, you see the heights, and then for two bodies that collide with each other. Let's look at the various interpretations of coefficient of restitution. When the value of E is equal to 1, it means the collision is elastic or perfectly elastic. But when the collision, when the value of E is equal to 0, that is, when the coefficient of restitution is 0, the collision is perfectly inelastic. And then when the coefficient of restitution is between 0 and 1, that is less than 0 and greater than 0 and less than 1, with 0 and 1 exclusive, then the collision is inelastic. Collision is inelastic. So this gives us the three types of collisions that we have. Three types of collision. Elastic collision, perfectly inelastic collision, and then inelastic collision. Let's look at them one by one. Elastic collision. We also call it perfectly elastic collision. Now, collision is said to be elastic when the colliding parties separate immediately after collision. In that case, momentum is conserved, kinetic energy is conserved, time spent on collision is negligible. The two bodies undergo elastic deformation. What that means is that they are able to regain completely their original shapes and dimension. And then the coefficient of restitution is 1. That is elastic collision. Then we have 2, inelastic collision. Inelastic collision. A collision is said to be inelastic when, let me make a little correction to something that I wrote in the other video in the seats, this one. You realize that I wrote an equation which was E is equal to H over capital H. But indeed, this equation was supposed to be written as this. You understand? So after I watched the video, I realized that I had made that small mistake, but I didn't cut that part off. I maintained it just to let you know that to err is human. It is human beings that make mistake. When you make a mistake, it's normal. It doesn't mean you should go kill yourself. You understand that? So when you make a mistake, just correct the mistake and move on with your life. All right? Good. So let us continue from where we left off. I had to go and pick my markers. So let us continue from where we got to. Now, we're looking at types of collision, and then we got to the second type of collision, which is inelastic collision. Inelastic collision. Now, collision is said to be inelastic when the colliding bodies stick together for some time, and then later they separate. So after the colliding bodies hit, they will stick together for some time, and then later they will separate. That type of collision is what we refer to as inelastic collision. Now, in inelastic collision, momentum is conserved, kinetic energy is not conserved because at the point where they stick together, some energy is lost. Another way that energy is lost is the two bodies undergo plastic deformation. So because they are unable to regain completely the original shape and dimension, energy is also lost. So 1, we say momentum is conserved, kinetic energy is not conserved, coefficient of restitution is between 0 and 1. Coefficient of restitution between 0 and 1, with 0 and 1 exclusive. And the two bodies undergo plastic deformation. What that means is that they are unable to regain completely the original shapes and dimension. And lastly, the colliding parties stick together for some time and then later separate. Exactly. These are the characteristics of inelastic collision. So when we say the collision is inelastic, this is what we mean. Now, in calculation, okay, so I'll get there. Then we look at number 3. perfectly inelastic. Perfectly inelastic collision. Now, collision is perfectly inelastic when the colliding parties or the bodies engaging in the collision stick together forever. When they stick together for a long period of time without separating, we say the collision is perfectly inelastic. In this case, characteristics. Momentum is conserved still, but kinetic energy is not conserved. And I know you know the reason why kinetic energy is not conserved. I said it in the previous type, which is inelastic. Momentum is conserved, kinetic energy is not conserved. Coefficient of restitution is 0. The colliding bodies stick together for a long period of time without separating, and the parties undergo plastic deformation, meaning they are unable to regain completely their original shape and dimension. So these are the 3 types of collisions and their characteristics. Good. So let us pick these 3 types of collisions, and then we apply the Newton's we apply the momentum conservation principle. Remember, we looked at the momentum conservation, the principle of conservation of momentum in the first episode of the Newton's laws of motion and momentum. Yes. So in elastic collision, when momentum is conserved, let's consider these 2 bodies. M1 moving velocity U1 colliding with another body M2 moving with velocity U2. We are looking at a situation whereby the 2 bodies are moving in the same direction. All right, 2 bodies are moving in the same direction. Good. So this is before collision. Now, after collision, the 2 bodies will separate and move with their own velocities V2 and V1. So because momentum is conserved, we say that M1 U1 plus M2 U2, that will give us M1 V1 plus M2 V2. That is when momentum is conserved. Now, when kinetic energy is conserved, when momentum is conserved, when kinetic energy is conserved, we say that half M1 U1 squared plus half M2 U2 squared is equal to half M1 V1 squared plus half M2 V2 squared. You know, kinetic energy is given by half mv squared. All right. So when kinetic energy is conserved, this is how we write the equation. And when momentum is conserved, this is how we write the equation. For elastic collision. Or perfectly elastic. Now, in a situation whereby the colliding bodies move in opposite directions before collision, for instance, when this body M2 is moving in this direction with velocity U2, all right, because velocity is a vector quantity, we take into consideration the direction of the motion. For that matter, because this one is moving this way and the M2 is moving in the opposite direction, the sign of the momentum of the second body M2 becomes negative like this. I hope that is clear. Good. So this one becomes negative. If after impact, let's take it after impact, V1 also decided to move in opposite direction, in its original direction like this. Sorry, it decided to move opposite to its original direction. While this one also moves opposite to its original direction. Remember that this one has already been made negative. Because it is moving here, it is negative. So when now it begins to move here, when the M2 begins to move here, it will become positive. because this direction has changed. Please listen to this. When M1 is moving in this direction, its momentum is positive. When M2 is moving in opposite direction, its direction is negative. Now they collide and M1 changes direction and move in the opposite direction of itself. So its momentum will have to be negated, will have to be negative like this. And the momentum of this one initially was like this and it was negative. So now when it is like this, it will have to be positive like this. I hope you get the principle. Usually this is what students find troubles with. They don't really know which one to make positive, when the equation becomes positive, and when the terms in the equation become negative. And that is what I'm trying to explain to you. Good. So when we have a situation like this, this is how the formula for the momentum will become. And the same thing applies to the kinetic energy too. Alright? The same thing applies to the kinetic energy because the velocities are going to change direction. I hope you understand that. But you realize that kinetic energy is a scalar quantity. It's a scalar quantity. So when the velocity changes direction and it becomes squared, if it is negative, it will still become positive. So the formula like this will not really become affected. I hope you understand that. Good. So the kinetic energy remains the same way. Then we look at the situation whereby the two bodies undergo inelastic collision. Over here in calculation, we treat both inelastic and perfectly inelastic together. The reason is that we only consider the situation whereby the two bodies are sticking together. At the point where they separate, we don't really consider it under inelastic. So we consider the situation whereby the bodies are sticking together. For that matter, we look at this scenario. M1 with velocity U1 moving in the same direction as M2 with velocity U2. This is before they collided. After they collided, they stick together, M1, M2, and move with a common velocity V. They stick together and move with a common velocity V. Good. So let us write the momentum conservation for this. So remember that kinetic energy is not conserved. So we wouldn't write an equation for kinetic energy. It's only momentum which is conserved. So in this case, M1, U1 for momentum conservation plus M2, U2, that is equal to, according to the momentum conservation principle. Let me state it again for the purpose of those that have not watched the previous video. The principle of conservation of momentum states that the momentum, that is the sum of momentums before collision, is equal to the sum of momentums after collision, provided there is no external force acting on a system of colliding bodies. So when two bodies collide, whether head-on or they collide, any form of collision, their momentums before collision is equal to their momentums after collision. That is when we sum them algebraically. Their momentum before collision and the momentums after collision are equal, are the same. That is what the principle of conservation of momentum says. Good. So this takes place when there is no external force acting on the body. Exactly. Good. So we say that M1 U1 plus M2 U2 is equal to M1 V plus M2 V. So because we have the same V, we factorize, they move with a common velocity, and their velocities are the same. We factorize that V out. That will give me M1 U1 plus M2 U2 is equal to M1 plus M2 all times V. Like this. Alright? Good. So this is how we have to write the equation so that we can use it to solve our example when the need arises. Now, let me bring in this. It is not always that the two bodies will be in motion. Sometimes one of the bodies will be moving because the other is not moving. So you have a moving body colliding with a stationary one. Let's suppose that M1 is moving, but M2 is stationary. It means that in this situation, the initial velocity of M1 is 0. So the initial velocity of the initial velocity of M2 is 0. So the initial velocity of M2 is 0. 0 times M will give us 0. So the formula will become something like this. And it is written as M1 U1 is equal to this. M1 U1 is equal to M1 plus V, M1V plus M2V. I hope you get a principle. So in a situation whereby one of the bodies is stationary and the other one is moving, then what we do is that the one that is stationary, its momentum is 0. So the formula becomes like this. The same thing can also be applied to this one. I hope that is clear. So these are the scenarios that your teachers are going to trick you with, that WAEC is going to trick you with questions. So when you are given a situation like this, I know you have an idea of how to handle it. So let us solve one or few examples on this. Then we say bye-bye to the topic. Good. So if you remember, in our previous episode, that is the first episode of the Newton's laws of motion and linear momentum, we were given a question. So let me get the question and then so this is the question that was given to us. So let us try and see how we go through this question. We are told that a ball of mass 200 grams is released from height 40 meters above the ground. If the ball rebounds to a height of 28 meters, find the impulse received by the ground. Solution. So let's solve this. In the first instance, the ball is released from the height. Let this be the ground level. 40 meters above the ground. 40 meters. The ball rebounds to a height 28 meters above the ground. Remember that in exam, some of these things that you do don't fetch marks, but they help you not to place right values at wrong places in equations. You understand that? Good. So don't waste too much time on these kind of sketches. It is the formula, the substitution, and the answer that we normally mark in. So don't waste too much time on some of these things. Exactly. Formula, make sure your formula is there, the substitution, and the final answer. Good. So we know that impulse I is given by momentum mv minus mu. That is when the change in momentum takes place in the same direction. In this case, the change in momentum is taking place in opposite directions. So this momentum will have to be negated. So the final formula will become I is equal to mv plus mu. Remember in that episode where I gave this question, I told you that in a rebound situation, this is how the formula for the impulse becomes. So we have the mass. What we need to do is to find the v and find the u, and then we put them here to get our impulse. So the velocity with which this object will hit the ground, all right? The velocity with which this object will hit the ground, we call it the velocity of impact. And the velocity of impact from linear motion is given by v is equal to square root of 2js. Okay, let me try and start from where I got this equation. You know, we are using one of the Newton's equations of motion, which states that v squared is equal to u squared plus 2js. So remember, the object is falling. So because the object is released, the initial velocity u is 0. So v squared is equal to 2js, where s is the height. So therefore, V is equal to square root of 2js. So V is equal to square root of 2 times 10, which is acceleration due to gravity, times the height, 40. So V is equal to square root of 800. So we punch the square root of 800. And that gives us 28.28 meters per second. So V is equal to 28.28 meters per second. Good. Then we find the initial velocity that was given to the object to move up in the rebound case. So in the rebound case, we still use the same equation. V squared is equal to U squared minus 2js. This time around, we are using minus because the body is going up. And as a body moves up, it moves against gravity. So the motion retards, all right? As the body goes up, its velocity decreases with time. So the acceleration becomes a retardation. That is the reason why the G is negative. So for that matter, but at the maximum height, V is equal to 0. At the maximum height, where you get to 28 meters, so we get 0 is equal to U squared minus 2gs. So U is equal to square root of 2gs. So U is equal to square root of 2 times 10 times 28. U is equal to 2 times 10 times 28, square root of 2 times 10 times 28. That will give me 23.66. So U is equal to 23.66 meters per second. All right. So this is the initial velocity U. This is the final velocity V. So now we put these two values in this equation, that we solve it. So therefore, the impulse received by the ground, I, is given by M into bracket V plus U. And that is going to give me the mass. 0.2. We divide 200 grams by 1,000 to convert it to kilograms. Into bracket 28.28 plus 23.66. So the impulse I is equal to, so we have 0.2 into bracket 28.28 plus 23.66, bracket close, and that will give us 10.388 newtons seconds. All right, the unit for impulse, impulse is force times time, so that gives us newton seconds, or 10.388 kilogram meter per second. This is how it can also be written. That's another unit for impulse. So when we are given a question like this, this is how we go through it. Let's look at one last question on the principle of collision. One last question on collision. So what I'm going to do is that after you have seen this video, try and solve a lot of examples, and then those ones that you are unable to solve, send it to me through the Facebook page, BJ's Physics Classroom. Just go to the page, BJ's Physics Classroom, post your question there, and then I will handle it for you. Good. So let's look at this one last example. Good. So we have another question to try it. We have another question which is on linear momentum and collision. A ball P of mass 60 grams loses 1/3 of its original velocity. If it's okay, so when it made a head-on collision with an identical stationary ball Q. If Q moves off in the same direction, in the original direction of P with speed 4 meters per second, find the original velocity of P. We want to find the original velocity of P. In other words, the initial velocity of P. So we are told that, solution, a ball P initially moving with velocity UP collides with a stationary ball Q. This is before. Now, after collision, P loses 1/3 of its original velocity. So P loses 1/3 of its original velocity. What that means is that the velocity that P moves with after collision is the original velocity of P minus 1/3 of that original velocity of P. P will move with velocity Vp, but that Vp is equal to the original velocity UP minus 1/3 the original velocity UP. Why? Because we are told that P loses 1/3 of its original velocity when it made a head-on collision with an identical stationary ball. So when it made a head-on collision with this identical stationary ball, it loses 1/3 of its original velocity. So we subtract that 1/3 of its original velocity from this to get the velocity that P moves with. And Q moves off with velocity 4 meters per second. Good. So this is before collision, this is before collision, and this is after collision. Remember, I have told you, this sketch and this information you write here only helps you to answer the question and get the answer correctly, correctly. But it doesn't fetch much. So do not waste much time on this. Good. Always think of the formula, the substitution, and the final answer. Thank you. So applying the principle of momentum to this. So let me evaluate this before. And what that means is that our VP is going to give us 2/3 of UP. So our VP is equal to 2/3 UP. Applying the principle of momentum to this question, MP UP plus, I'm supposed to add the momentum of this, but this one initially was stationary, so its momentum is 0. That will be equal to MP VP plus MQ VQ. So apply the principle of momentum, because they move in the same direction, both of them are positive. This one was stationary, so its momentum is 0. Good. So we put in the values. But remember, the balls were identical, so even this mass is not important. Because the balls are identical, MP is equal to MQ. For that matter, all the masses will cancel out, and finally we get UP is equal to VP, but you know VP is given by this. That will give me 2/3 UP plus VQ, which is 4. Then we solve. Remember that the mass will cancel out because MP is equal to MQ. All right, MP is equal to MQ. So the masses will cancel out. That is why the final equation has become like this. Now, we take this one across the equals and to subtract from this. That will give us UP minus 2 over 3 UP is equal to 4. Good. So when we subtract this one from this, that will give us 1 over 3 UP is equal to 4. Therefore, UP, which is the original velocity of P, is equal to 3 times 4. That is equal to 12 meters per second. It means that the original velocity of P, is 12 meters per second. Good. Thank you very much for being part of the BJ's Physics Classroom. Like I have always said, if you haven't subscribed to my YouTube channel, please subscribe to the channel. The channel is BJ Online. Thank you very much for being part of the show. Till I see you again with another topic. It's your friend, BJ.